Hi, I'm Landon. I'm going to tell you a joke. Why did the dinosaur cross the road? Because chickens haven't evolved yet.
Hi.
Hi, it's Max.
Okay, so that was Landon and Max. Let's get back to some mathematics. All right, so we're going to talk about related rates. In class, we didn't really go through the steps, so I want to start there. So when we have a related rates problem, we're really going to kind of follow some very significant steps. So step one is obviously read the question, because if you don't read the question, you're not going to know what's going on. And then often what we want to do is rewrite the given information into some algebraic terminology, or maybe draw a diagram that helps us put the information somewhere in a visually appealing context. The next thing you want to do is, once you have that equation, you want to take the derivative of both sides and leave behind d something dt when you take that derivative, because now we're going to take the derivative with respect to time, so we're really doing this implicitly. Substitute everything you have in. If you have more than one unknown variable left over, you got to use your noggin to figure out what's missing. That's like Pythagorean theorem, or maybe there's information you missed, or maybe something zero that you didn't realize. And then last but not least, solve for what you're missing. So let's move ahead here. I am going to jump to question number 4. So in question number 4 here, it says we have the volume of a sphere is given by V equals 4/3 pi r cubed, and S equals 4 pi r squared. And if you hear the whining, that's Max, who's coming back to want some food. Hold on a moment. And it says the surface area here of the sphere is changing at a rate of 30 square inches per second. So I'm going to say that means that ds dt equals 30 square inches per second. And at that moment, the radius is 8 inches. What is the rate of change of the volume of the sphere? So if I want to know the rate of change of the volume of the sphere, I want to take the derivative of both sides of this equation with respect to t. So I'm going to do that. And I'm going to say, well, dv dt equals 4 pi r squared dr dt. And then if I plug in what I know, I have 4 pi r squared. And I don't know dr dt, and it's definitely not given to me, but they've told me about surface area, and I haven't used it yet. So maybe I should use the surface area now. So I'm going to take the derivative of surface area with respect to time. And I'm going to get ds dt equals 8 pi r dr dt. And they told me ds dt is 30, so I'm going to substitute that. So 30 equals 8 pi times 8 dr dt. And there we go. Now I can solve for dr dt and substitute it in. So dr dt is 30 divided by 64 pi. I'm going to substitute that in over here. And dr dt is 30 over 64 pi. Max, don't touch the pen, little buddy. And then let's see, 8 and pi here becomes pi and 64. Pi and 64. So dv dt is 120. And it doesn't say to give units of measure, but it's worth doing. So this is volume with respect to time. We're dealing in inches here, so that'd be cubic inches per second. There we go. So let's go on to the next one. Now, cones are special. They're very special. And when we deal with cones, we have to look for a couple different things, and I'm going to walk you through that right now. Max, you're killing me, dude. You're just killing me. So why are cones special? Well, in a cone here, I have this right triangle, this H and R. And if I come up here and I shortened the cone and just took a small section of it, I'd have a new R and I'd have a new H. But the thing is, this angle right here is the same for the top triangle as it is for the whole triangle. And this right angle is the same for the top triangle and the whole triangle. These two triangles have a similarity, which means H over R equals H2 over R2. And what that really means for us is it means we can rewrite.
Give me my book. I'm wondering.
it means we can rewrite our equations in terms of one variable because h over r is a constant for the entire cone. So let's see how that works here. Water is being poured into a cone-shaped cup. So here's a cone-shaped cup. Worst shape of a cup ever, but still it works. So a cone-shaped cup, and I've got some water inside here, and the initial cup has a height of 6 inches. And let's see, a diameter of 4 inches. And if the water is flowing in, so I've got water coming in here at a rate of 5 cubic inches per second. If that's pouring in at 5 cubic inches per second, how fast is the depth of the water in the cup changing? So I want to know, how fast is this changing at the instant when the depth is 2? So it's 6 total, but we're saying this right here is 2. What am I going to do? Well, option 1 is to say the volume of a cone is 1/3 pi r squared h. And if I were to take d dt of this whole thing, I'd have dv dt equals 1/3 pi. Now I need a product rule. The first times the derivative of the second plus the second times the derivative of the first. That's a lot of variables, and it's workable, but it's not very fun. Instead, what I'm going to do is say, all right, I have this cone, 1/3 pi r squared h. However, in this cone, my r initial was 2, and my h initial is 6, so that means h equals 3r. So if I wanted to write everything in terms of r, I could replace this h with 3r. However, I want dh dt, so I want to be in terms of h, which means I have to solve for r, so r is h over 3. So I can rewrite the volume for this cone as 1/3 pi r squared h, which is going to give me v equals pi over 27h cubed. And then when I take d dt of both sides, I end up with dv dt equals 3 pi over 27h squared dh dt, which really says, okay, dv dt is the rate of change of the volume of the cup, and I'm increasing the volume of the water in the cup by 5 cubic inches per second. This is pi over 9. H at the time that we're dealing with is 2. And dh dt is what I'm solving for. So I end up with dh dt equals 4 pi over 9, and that equals 5. So this would be 45 over 4 pi, and that is my dh dt. And then what would those units be? So my units here, its height would be in inches per second. Now you may want to say, wait, Mrs. Vibber, you said dv dt is 5. The volume of this cup isn't changing. You're right, the cup itself isn't changing, but what I'm really looking at is the volume of the conical shape of water that's been poured into the cup right now. All right, so one more of these, and then I'm going to stop, I think. So we have one more. Coffee's draining from a conical filter into a cylindrical coffee pot, at the rate of 10 cubic inches per minute. How fast is the level in the pot rising when the coffee in the cone is 5 inches deep? All right, so let's deal with one thing at a time. So I have my cone-shaped filter up here, and it is 6 inches across and 6 inches tall. So let's see, my radius would be 3, so r equals 3, h equals 6, so h equals 2r. And let's see, it's draining into the pot at 10 cubic inches per minute. So water is coming out at 10 cubic inches per minute. Let's see, how fast is the level in the pot rising when the coffee in the cone is 5 inches deep. So this is going to be 5. Okay, so what can I do with this? Well, let's see here. We probably need to know how fast the level in the cone is falling at that moment. Well, let's see. How fast is the level in the pot rising? So let's talk about the pot now. I'm done with the cone. I want to deal with the pot now. So I have my coffee pot, and it's a cylinder. And as my cylinder fills up, okay, the volume of a cylinder is pi r squared h. And so if I want to figure out how fast the level in, let's see, how fast the level in the pot is rising, I want to know what dH dt is. So I'm going to take d dt here and see what else I might be missing. So if I take d dt of both sides, I have dv dt equals a product rule, so pi r squared dH dt. So there's the first times the derivative of the second, plus the second times the derivative of the first. And let's see, dv dt for the coffee pot. Well, the coffee in the pot's coming from the cone, so my cone is increasing the volume in the pot by 10. And then I have pi r squared. So let's see, the radius at this moment, well, it's 5 inches high. The radius is always half the height. So my radius would be 2 point, oh wait, no, this is my coffee pot, okay? I'm gonna lie and pretend that I did that mistake on purpose so I could talk about it, but really it's just because I'm distracted by my kids. Okay, so I have R for the coffee pot down here. So let's see, what's my coffee pot R? My coffee pot R is 3, and that's squared. And dH dt for the coffee pot is what I'm looking for, plus the height in the coffee pot. I don't know that. The radius I know. dr dt, wait. dr dt for the coffee pot, that means at what rate is the radius of the coffee in the pot changing? It's not. It's a cylindrical coffee pot. Its radius is what it is, no matter where I am. We're kind of assuming that the coffee drips down, splashes out, and flattens immediately. So this is a big old 0. So dH dt for the coffee pot is 10 over 9 pi. Okay, so I have that, and it says then, how fast is the level in the cone falling? So I want to know what's dH dt over here. So the volume of the cone is 1/3 pi r squared h. I want to be in terms of h, so I'm going to write this as r equals h over 2. And then v equals 1/3 pi h over 2 squared times h. So v equals, let's see, pi over 12 h cubed, which means if I take the derivative of both sides with respect to t, I have dv dt equals pi over 4h squared dH dt. Oh my goodness, I'm running out of room here. So let's see, dv dt, well, the volume of coffee in the cone, the volume's leaving at 10 cubic inches per minute. So this is going to be negative 10. Pi over 4. H for the whole cone was 6, but for the water was 5. So I got to use the 5. Because again, I'm not dealing with the volume changing of the conical filter. I'm dealing with the conical shape of water in the filter. So the water has a height of 5. That's squared. Now I need dH dt here. So negative 10 equals 25 pi over 4 dH dt, which means dH dt is negative 40 over 25 pi. Whatever that is a number. It's some number. I don't know what number it is. You can type it in your calculator if you really want to know. Okay, so long story short, cones are very special, so treat them that way. I'm done, so let's see. Mrs. Vibber needs to give you guys a joke. What is Mrs. Vibber's joke going to be? It is going to be, why did all the bakers turn up to the math lesson? Because they heard they were going to learn about pie. I got that joke from an Amazon Alexa, as nerdy as that is. All right, everybody say bye, students.
Bye!